So when we had our little balls charged up, one was Q1, one was Q2, and there were clearly forces pushing them apart, right? So we can draw the forces like this. The force of charge 2 on charge 1, which we call F21, is a vector pointing to the left, and it's equal to K times Q1 times Q2 over R squared times a unit vector, R hat 2, 1. So that's a vector that goes from the charge 2 toward charge 1. So this is just a direction in space. Likewise, F12 is K Q1 Q2 over R squared R12. So Newton's third law is still in effect. For every action, there's an equal and opposite reaction, right? So you could think of this force as being the reaction force to that one if you so choose. But so you can use Newton's third law to do these electricity problems. And I'd like to emphasize, though, that these R's with a little hat on them carry no units of distance. They're dimensionless. They're just a direction in space. Even though it looks like, Professor Conway, why do you have R in the numerator? Doesn't it cancel the R in the denominator? No. This is a completely different mathematical object from the R here. This is a distance squared. This is just a direction in space. Now we possibly confusingly chose R to represent that distance. We could have chosen D, the distance between the two charges, to represent the distance apart. Maybe that would be better. I don't know. You decide. But it's so often written as 1 over R squared, and you're going to see that in the text and in a lot of the problems, that we stick with that notation. But remember, those things just tell you the direction only. Also, now, so far we were just talking, in the beginning we were talking about electric fields. Where did the electric field go, right? Well, turns out we can regard this force on this charge as coming from the electric field created by the other charge, and vice versa. So let's do that. Let's see how that comes out. We can do that in a minute. First, though, we want to talk about the analogy that we have with the gravitational force, which you encountered in Physics 7a. And in that case, the gravitational force is Newton's constant G times the product of two masses divided by R squared. Now, unfortunately, the gravitational force is always attractive. It would be really fun to have anti-gravity, but no one's figured out how to do that yet. That would require apparently making negative masses, but we don't know how to do that either. So anyway, masses are always positive. That means the force of gravity is always positive, and by the convention there, that's an attractive force. That's different from how we do it with the electric force, where we have the product of two charges, which could be positive or negative. If they're both negative, the force is positive. We call that repulsive. And if one of them is negative, then it's an attractive force. That's just our convention. But let's just forget about the sign of the force and talk about the magnitude of these two forces. First of all, note that these constants of nature have similar structure to them in the sense that, well, it's Newton meters squared per kilogram squared here, and Newton meters squared per coulomb squared here. So, we use the MKS system, meters, kilograms, seconds. Now we're adding this unit of coulombs to our list of things. We're going to define what we mean by a coulomb shortly using mechanics. But also note that this is 10 to the minus 11th for gravity, and this is 10 to the 9th for electricity. And the fact of the matter is, electric forces are a lot bigger than gravitational forces. Well, what do we mean by that? Doesn't it depend on what you're talking about? Well, yes, and we're going to do a calculation in a second. But realize one thing, that sitting there in your seat, the gravitational force is not ripping you apart, right? You feel a pressure from your seat. Gravity is pulling on you downward, and the seat is pushing upward, equal and opposite to gravity on you, and you can feel that, but your whole body isn't being torn apart by gravity. So gravity is not strong enough to tear apart the electric forces holding your molecules together. if you drop an object on the floor, it doesn't keep going to the center of the Earth, which it would if the gravitational forces were much greater than the electric forces. Still, we need to do a more revealing calculation. So let's do this clicker question. This will require punching a bunch of numbers into your calculator, so you need to get that out. And it takes a little bit of time to get it right. So you can try to do that. So we have 2 protons in a water molecule. And it turns out that they're 0.3 nanometers apart. Okay? Now I'd like you to calculate the ratio of the electric force between those 2 protons and calculate the ratio of that to the gravitational force between them. Which is bigger, the electric force or the gravitational force? Now we already said on the previous slide, electric forces are a lot bigger. But how much bigger? And it's orders of magnitude, but how many? So go ahead and do the calculation with the numbers given there, and I'll try to do the calculation too.